equations of motion. And next week is probably going to be mostly a review on Tuesday, and I'm also going to hold the discussion section on Wednesday. We're going to solve problems involving systems of rigid bodies and systems of particles and rigid bodies. Do that on Tuesday. Wednesday, maybe solve some previous exams, see if you have any questions. And on Thursday, we're going to have our final exam during class time. Ninad announced on Ed, I think he posted an announcement that he's going to have an online review session on Friday, tomorrow from 5 to 6, right? So for extra practice, hop on onto that. Great. So let's start with Lagrange's equations of motion for a system of particles. So today is not meant to be a thorough, complete explanation of Lagrange's equations of motion. It's just an introduction. Okay. So again, it's a rough introduction, but introducing us to the subject of analytical mechanics. When Lagrange introduced his book on analytical mechanics, he was bragging that the book did not involve any geometry, any diagrams. It's purely analytical. And that's one of the advantages of Lagrange's equations of motion and its derivatives, that it's mostly analytical, meaning that it can be easily translated or more readily translated than what we've been learning so far in ME 104 into writing it as a computer code, solving differential, like obtaining the differential equations analytically, more than geometrically. Okay, so before we dive into Lagrange's equations of motion, I need to introduce a few terms. First, let's talk about constraints. There are many categorizations of constraints. Constraints that depend on time, constraints that do not. The differentiation I want to do here is between holonomic and non-holonomic constraints. So holonomic constraints are also known as integrable constraints, whereas these are non-integrable. Okay. There's a difference between a holonomic constraint and a holonomic system. So here we're looking at just holonomic constraints. So holonomic constraints are integrable, meaning that they can be written in terms of position coordinates. So holonomic constraints are integrable constraints that can be written in terms of position coordinates only, whereas non-holonomic constraints, they're written in terms of velocity coordinates and cannot be integrated to be written in terms of position coordinates only. Okay, and let's look at examples. Okay. Example that is considered a particle on a surface. Okay, so again, we're introducing Lagrange's equations of motion. Before that, I want to differentiate between two types of constraints, holonomic and non-holonomic. A holonomic constraint can be written in terms of position coordinates only, whereas non-holonomic constraints cannot. So for example, if we have a particle that is constrained to move in the horizontal plane z equals to 0, is that constraint holonomic or non-holonomic? Holonomic. Why? Exactly. Z equals to 0 is a position coordinate. Okay. Now, that constraint z equals to 0 can also be written as velocity along z is 0, like z dot is equal to 0. So that's written in terms of velocity. However, it can be integrated to be written in terms of position, meaning that z is 0. Does that make sense? So that constraint, even though I could write it as z dot equals to 0, I could integrate it to get z equals to 0. So that constraint, even though it might be written in terms of velocity, is still integrable. Can be written in terms of position coordinates. But that's not the case for all constraints. Let's continue with more examples. Let me consider two particles connected by a rigid rod, such that the length of the rod is L. Is this constraint holonomic or non-holonomic? To be able to answer this question, we need to think about how can I write this constraint mathematically? It's holonomic, right? Why? How can I write it down?
R1 minus R2.
Exactly, the magnitude of the position vectors, R1 minus R2 minus L is equal to 0. So this is a constraint that I've written in terms of the position coordinates, the position vectors. So it is a holonomic constraint. This one too was holonomic. Can anyone think of any other holonomic constraints? Yes. For a projectile, the projectile, what would be the constraint acting on the motion? The projectile is quite unconstrained, right? Because, yeah, there are no constraints acting on it, so wouldn't quite apply. Now we can think of the projectile as moving in a like planar motion, but that's just not an applied constraint. That's an artifact of just solving the differential equations. But any other examples of systems subject to holonomic constraints?
Like a pendulum.
A pendulum, a simple pendulum, exactly. That says that the length between of the cord, the pendulum cord is constant. So if we were to take a cylindrical, a polar coordinate system like this, L, this means that R dot ER minus L is equal to 0, right? That's R minus L is equal to 0. That's the holonomic constraint written in terms of position variables. If you have a particle moving on a cone, on a cylinder, on any surface, that's also a holonomic constraint. Does that make sense? Any questions so far? And now what is an example of a non-holonomic constraint? Knife edge constraint. So consider I have this previous system still subject to the holonomic constraint that R2 minus R1 but I could add a non-holonomic constraint which could be that V2 dot R2 minus R1 equals to 0. What does this constraint mean physically? Sorry, let's not do this. Let's introduce the constraint this. L Ex Ey V2 dot Ey is equal to 0. That's the knife edge constraint. What does it mean? Can anyone guess what this constraint does from the equation and from the name of it? V2 is constrained to move how? It cannot have Ey components, it's constrained to move along Ex. So it's, for example, when you're skating, ice skating, you cannot move your leg sideways. You can only move it along the skate. So that's the knife edge constraint. That's the constraint applied here. You can also kind of approximate if you have a bicycle and you're rolling a bicycle, riding a bicycle, the front wheel you can turn it however you want, right? But the back wheel is constrained to move along the bicycle path, so that's a knife edge constraint. And this constraint turns out to be non-integrable. I cannot write it in terms of position coordinates. It can only be written in this way in terms of velocity coordinates. So this is a non-holonomic constraint. That's a non-holonomic constraint. Now, there are criterion that can be applied to this constraint to determine if it's integrable or not, because sometimes you might not be able to visually identify whether a constraint is integrable or not if it's given in terms of velocity coordinates. This method to determine whether a constraint given in terms of velocity coordinates is integrable or not is called Frobenius's integrability criteria. So there's a method to the madness. We can actually verify using a theorem that this constraint is non-integrable. However, the particular theorem is beyond the scope of the class. I won't go into it. Any questions? Okay. So that's our discussion about constraints. Whenever we have constraints, we have constraint forces. So let's move our discussion to Lagrange's prescription of constraint forces. So again, all of this is being applied to a system of particles. So let us say this. Consider a system of n particles. My origin, my system of particles, V1, V2, Vn. Consider a constraint written on the system. Constraint applied to the system. Written as F1 dot v1 plus f2 dot v2 plus fn dot vn is equal to 0. Then okay, so this is Lagrange's prescription for a constraint force. So a constraint can be written in this way. We can write the constraint force in this way. Let us verify or check whether what we've learned so far in the course aligns with this prescription of the constraint forces. So for example, if I have the same system here of one particle, a particle moving on a surface, the constraint acting on it is z equals to 0. How can I write this constraint in terms of the form above? Remember, it's just one particle here, so I'm just going to have the first term. How can I write this constraint in terms of, or in the form of the constraint above? It's just going to be one term. What is it? Before I write the constraint force, I want to figure out what the constraint is. Yes. So I want to figure out what this constraint is. It's written in terms of velocities, right? Now this constraint is written in terms of positions. How can I write it in terms of velocities? I can differentiate it, right? So I'll get z dot is equal to 0. So the particle is moving on the plane z equals to 0. Its velocity is z dot is equal to 0, which is, this can be written as the velocity of the particle dotted with which vector? Ez. V dot Ez is equal to 0. So now I have this constraint written in terms of the form above. Now, according to Lagrange, what is the constraint force acting on this particle? According to Lagrange, the constraint force acting on the particle is some scalar mu along which vector? Ez. Great. Does this match with what we've learned from this course so far? If I have a particle moving on a surface, if I were to ask you before this lecture, if I have a particle moving on a surface, a particle on the table, what is the constraint force acting on this particle? Or what is the force that enforces the constraint that the particle is moving on this plane? It's going to be the normal force, right? And what is the direction of the normal force? It's perpendicular to the table. If the surface is z equals to 0, then the normal force is along Ez. So this constraint force is none other than the normal force. okay? However, I was able to obtain this force without drawing a free body diagram, without thinking analytically. Just by writing the constraint, applying Lagrange's prescription, I was able to get the constraint force. Let us see if this still works for the other system. For the system of the two particles attached by a rigid rod of length L. If I were to draw the free body diagram of these two forces, of these two particles, M1 and M2, what would be the forces acting on these particles? You have weights and normals, correct? Weight, normal, 1, 1, and 2, 2. And what is the force due to the due to the constraint? Yeah, there's some tension force in the rigid massless rod. So a tension force T and a tension force minus T that's gonna point along the length of the rod. So ideally what I want is that when I use Lagrange's prescription for the constraint force between the two rods and obtain the corresponding force, I should get T. I should get a force acting on particle 1 along the rod and equal and opposite force acting on particle 2. So let us see. We've written this constraint as R1 minus R2 minus L equals to 0. Step 1, how can I write it in terms of this, in this form? Take a minute, think about it, chat with your neighbors. How can I write it in terms of this form so that I can get the constraint force? Any ideas? Ideas? I will give you a hint that this magnitude can be written in terms of a dot product. R1 minus R2 dot R1 minus R2 minus L squared is equal to 0. So then how can I write it in terms of velocities? Maybe differentiate. Take a minute, think. Ideas? Okay. So it's just that we can write this in terms of R1 minus R2 or as R1 minus R2 dot R minus R2 minus L squared equals 0. I can differentiate this. I can differentiate this dot product. I will get two terms, but they're going to be equal, so I can add them. I will get V1 minus V2 dot R1 minus R2 is equal to 0, right? Which I can rewrite in the above form, V1 dotted with R1 minus R2 plus or minus, actually, R1 minus R2 dotted with V2 is equal to 0. So is this form the same as the form above? Yes. So what is the corresponding constraint force? Here we have two particles. We're going to have two forces, one on each particle. What is the force acting on particle 1? Exactly, mu R1 minus R2. Does that make sense? Any questions? Take a minute, chat with your neighbor, make sure they're okay with this. Need questions. Yes?
In the original, like, F1 dot V1 equation,
Mhm.
like, all the constituents, can that be just written as the position vectors? Or, like, I'm confused how you get to the R1 minus R2 for F1.
I'm just comparing these two forms. I start with the constraint and I write it in a form that looks like the other one. By the way, this is not magic. There is a method to the madness, but it's beyond the scope of this course. It is what you would learn in intermediate dynamics, for example. But today what we're doing is just we're learning how to apply these equations, giving us a perspective of other methods in dynamics, other than the Newton-Euler equations. We've been doing the whole semester. Any other questions? So that's the force F1 acting on particle 1. There is a force F2 acting on particle 2. What is it? Yeah, it's going to be minus mu R1 minus R2. So notice that this force is directed along the rod, right? Because R1 minus R2 is a vector along the rod. And the force on 1 is minus the force on 2. It's opposite to the force on 2. So this confirms what we've expected. It aligns with our expectations with what we want, right? Very well. Okay. Okay, so we're going to consider a system of particles. For simplicity, I'm going to say that it's subject to one constraint, but the same method applies if it were subject to multiple constraints. If the system is subject to multiple constraints, you would have multiple constraint forces. They would each have a different magnitude, but you prescribe them in the same way. You list the constraints, and for each constraint, you have a corresponding set of constraint forces acting on each particle. Okay, so again, for simplicity, we're going to consider one constraint acting on the system. Consider a system of particles subject to one holonomic constraint. Okay, consider a system of particles subject to one holonomic constraint. We're going to write a list of the generalized coordinates and generalized velocities of the system. Question. If I have a system of n particles, in general in space unconstrained, how many degrees of freedom does this system have? What is it? If I have one particle, how many degrees of freedom does it have? 3. 2 particles, 6. It's in general, for n particles, I have 3n degrees of freedom. So the number of generalized coordinates needed to describe the motion of the system is going to be 3n. However, I'm going to arrange these coordinates in a special manner. So I'm going to put an array of generalized coordinates, q1, q2, q3n. I'm gonna let this last coordinate be equal to the constraint. Actually, call it subject to M holonomic constraint. I'm going to keep it a little bit general. Let the last okay, so I have a system of n particles, 3n degrees of freedom, m holonomic constraints. So how many, okay, no, let's repeat. I have a system of n particles, 3n coordinates, m holonomic constraints. How many degrees of freedom does the system now have? So for example, if I have the simple pendulum, that's one particle, 3 coordinates, but it's subject to 2 constraints, that the length of the pendulum is constant and that it's moving in the plane. So how many degrees of freedom does the simple pendulum have? 1. In general, for a system with 3n coordinates, m holonomic constraints, the number of degrees of freedom is going to be 3n minus m. Is 3n minus m. So what I want to do when I prescribe the generalized coordinates, for example, for the simple pendulum, I will let the first coordinate be the unconstrained coordinate, theta. And then I have 2 more coordinates that are the constraints, z and then r. Sorry, I'll define a new coordinate which is equal to a, and I'll call a is r minus l, and that's equal to 0. Z equals to 0. So these are the 2 constraint coordinates. Constrained coordinates. And this is the free DOF. So I have the simple pendulum that's subject to 2 constraints, that it's moving in the plane, z equals to 0, and then the length of the cord is constant. R minus L is equal to 0. So I'll define my coordinates, my constraints to be coordinates. So z equals to 0, that's itself, and then r minus L is equal to 0, let that be a, and that's my third generalized coordinate. Okay. For example, another example, if I have the simple harmonic oscillator, it's moving in rectilinear motion on a straight line. How many degrees of freedom does this simple harmonic oscillator have? 1 degree of freedom, right? And how many constraints? 2. Let me take Ex, Ey to be like this. According to this rule, how should I prescribe the generalized coordinates for this simple harmonic oscillator? I can just use x, y, and z, where here x is the degree of freedom and the 2 constraints are y equals to 0 and z equals to 0. So 3n is 3 because n is 1 and m is 2. So the number of degrees of freedom is 3 minus 2, which is 1. I'm also going to define the generalized velocities, which are the derivatives of the generalized coordinates. For example, Q, U, the set of generalized velocities are U1, U2, U3, and where UI is the derivative of QI. Oops, I wanted to do something. Actually, I wanted to use superscripts. Sorry, let's fix that. Here too, E. Okay, and these are generalized velocities. Notice that, okay, why do we restrict our attention, or why do we restrict ourselves to holonomic constraints? Can anyone guess based on these rules? Why do I only consider holonomic constraints? Why do I make this restriction? Yes.
Is it just to reduce the amount of work you have to do to solve it? Is it just to reduce the amount of equations you have to use to solve it? Or?
Yes, it helps in this way. But remember how I said that the generalized coordinates, I want them to be equal to the holonomic constraints, or equal to the constraints. So if the constraints were not holonomic, if they were non-holonomic, then I cannot write them in terms of position coordinates. They're only written in terms of velocity coordinates. So I wouldn't be able to set the generalized coordinate to be equal to the constraint. Does that make sense? So I have this requirement here that I want the last m coordinates to be the m holonomic constraints. If the constraints were non-holonomic, then I cannot write them in terms of position vectors. Then I cannot write them, I cannot use them in the generalized coordinates in this way. Okay. Okay. Does that make sense? Any questions? Now let's introduce Lagrange's equations of motion. Okay. Okay. So these are Lagrange's equations of motion for a system of particles. How many equations do I have in total? It depends on the number of generalized coordinates, right? And generalized velocities. So I, here goes from 1 to 3n, the number of QIs and UIs. So I have 3n equations. Let's look at an example. Apply this to simple pendulum. Okay, the simple harmonic oscillator. The simple harmonic oscillator. Simple harmonic oscillator. I'm going to take my origin to be at the unstretched, at the free end of at the mass when the spring is unstretched. Take O to be at M when the spring is unstretched. What is T, by the way, in these equations, in Lagrange's equations? Yes. Exactly, it's the kinetic energy. So to be able to calculate Lagrange's equations of motion, I need to find my array of generalized coordinates, which I've found there. Q is equal to x, y, z. And I need to write my kinetic energy. What is kinetic energy? It's half mv dot v, right? T is half mv dot v, which is half m vx squared plus vy squared plus vz squared. My array of generalized velocities here is going to be u equals to vx, vy, vz. What are the constraints acting on the system? Y equals to 0 and z equals to 0. These are the constraints. Then we have corresponding constraint forces. So this I can write as v dot ey. And this I can write as v dot ec equals to 0. So what is the constraint force due to this constraint here acting on the particle? Yes. Mu ey, actually. And since I'm going to have 2, I'm going to call it mu1 ey. And what's the constraint force due to this constraint? Mu2 easy. So you can think of this practically as two normal forces, one from below and one from the sides, so that the pendulum is constrained to, so that the simple harmonic oscillator is constrained to move in rectilinear motion along the straight path. Okay, so now I go ahead, I apply Lagrange's equations. The first one, so I'm going to have 3 equations, right? Let me write them down. D by dt, del t by del vx, minus del t by del x is equal to, here it's just one particle, so f1 or f dotted with del r by del x. D by dt del t by del vy minus del t by del y is equal to f dot del r by del y. Easy. Okay, I want to pause a minute, think about this, and I need questions. Any questions? Questions? I have a question. So what are the forces acting on this system? We have the constraint forces, but is that it? We have the spring force and we have the weight force. So these are just applied forces, not constraint forces, that we need to add to F. So F is actually Fc plus the applied forces, which are the weight, and the spring force, minus Kx Ex. Now, you might tell me here that the whole point of Lagrange's equations of motion is not to use free body diagrams, not to think of the directions of forces and so on, not to use geometry. And the answer is, you're right. We're going to figure out a way to obtain these forces without geometry. It's going to have to do with the fact that these are conservative forces, and they can be obtained by taking the gradient of the potential energy, right? Okay. So let us apply this equation here. One more thing I want to say is R is Xex. Okay, I want to apply this equation step by step. D by dt. What is the partial derivative of the kinetic energy with respect to Vx? Not quite. This is the kinetic energy, right? Half mvx squared plus vy squared plus vc squared. mvx, right? Okay. Now, what about the derivative of the partial kinetic energy relative to x? Now does the kinetic energy depend on x at all? No, it depends on Vx, but not x. So what is this partial derivative going to be? 0. Okay. Minus 0 is equal now to f, which is this. Okay, dotted with del r by del x. What is del r by del x? Ex. Right? So at the end from this I get minus kx. Minus kx. If I were to fix rearrange, I'll get that mv dot x or max is equal to minus kx. What is this equation here? Are we familiar with it? Yes, of course we are. It is the equation of motion for the simple harmonic oscillator. That's what we would get from F equals ma projected along Ex for the simple harmonic oscillator, right? Now let's apply the same equation along y and z. Along y, I'll get d by dt. What is partial t partial vy? Mvy, exactly. What about partial t partial y? Minus 0 is equal to fc, which is, f, which is fc minus mg z minus kx ex dot, what is del r by del y? Ey, right? And the dot product between the two is just mu1. So from here, I get that MAY is equal to mu1. But if I enforce the constraint that y is equal to 0, Vy is 0, Ay is 0, I get that Ay is 0, so mu1 is equal to 0. I enforce the constraint now. Okay? Take a minute, please do the third one. Let me know what you get for the third equation. The third equation should enable you to solve for the constraint force mu2. Mm-hmm.
In the equation where we're writing mgec,
Mm-hmm.
is there a reason why?
Oh, it should be Ey, sorry. Let us fix something that the weight force is along Ey. If I take Ex and Ey to be like this, then this will be equal to Ey. So I will get that MAY is equal to minus mg plus mu1. This Ay is 0, so mu1 is equal to mg. So I solve for the constraint force mu1. Find mu2, please. What is mu2?
0.
Yes, mu2 is going to be 0. D by dt. Oops. Okay. Any questions? So let us observe what we get from Lagrange's equations of motion. So this system had 1 degree of freedom, 2 constraints. Because we arranged our generalized coordinates in this fashion, the first 3n minus m coordinates are the degrees of freedom, and the last m coordinates are the holonomic constraints. Then when we solve Lagrange's equations of motion, the first 3n minus m equations are going to be the equations of motion, and they're uncoupled from the constraint force. And the last 2 equations, the last m equations, are going to be equations for the that are going to give us the holonomic constraint force. So we have this nice decoupling between the equations of motion and the holonomic constraints, forces. Let us make an edit to the Lagrange's equations by introducing the Lagrangian. Okay. We can introduce the Lagrangian, which is the kinetic energy minus the potential energy. We can rewrite Lagrange's equations of motion in terms of the Lagrangian. These are going to be d by dt del L by del ui minus del L by del qi is equal to the sum k equals 1 to n, sorry, small n, of fk okay, but not the same fk, it's fk non-conservative. Okay, so what I'm doing over here is I'm separating the forces into F conservative plus F non-conservative. And this non-conservative force, I can write it, sorry, this conservative force, I can write it as the gradient of the potential energy. We explained this before when we introduced potential energies. Plus F conservative forces. And this term here enters into Lagrange's equations of motion through the Lagrangian. So on this side, F becomes just F non-conservative K. So let's redo this problem using this form. I'm going to have to write the Lagrangian. T is still the same. Sorry, let's write L is T minus U. The kinetic energy T is still the same, half mvx. So that's an example for the simple harmonic oscillator. L is T minus U. T is half m Vx squared plus Vy squared plus Vz squared. Now what's the potential energy here? How many conservative forces are acting on the system? To have the spring force and we have the weight, okay? So the potential energy due to the spring force is half k x squared, and the potential energy due to the weight is mgy. Now let's apply Lagrange's equations of motion. D by dt del L by del Vx minus del L by del X is equal to, here's just one force, F non-conservative dot del R by del X. What is F non-conservative here? So previously we have that we had F to be Fc plus these conservative forces. What does F non-conservative become? FC. It's just Fc, right? Fc, which is mu1 Ey plus mu2 Ez. Here. Okay, so would you please go ahead and calculate this equation and let me know if you get the same answer as here? You should. You should. Okay, let's take 2 minutes. Let's do this. Did you get the same answer? Okay. Did anyone get the same answer? Yeah? Yeah? So yes, you actually do get the same answer from this form of Lagrange's equations of motion, which uses the Lagrangian, embeds the holonomic, embeds the conservative forces on this side of the equation, the left-hand side. Okay, so the comment I was making before about the fact that in both formulations, this and this, the first three n minus m equations are going to give you the equations of motion. The last m equations are going to give you the constraint equations. Sometimes we do not care about what the constraint is. We just want to calculate the equations of motion. So we just want to calculate the first 3n minus m Lagrange's equations of motion, Lagrange's equations. In this case, we don't have to, or in this case, we don't have to take derivatives of Vy, Vz, y, and z. So we can simplify our analysis by enforcing the constraints in the kinetic energy and in the Lagrangian from above, initially. So, which board should I erase? This one. Okay, so if I'm just interested in the equations of motion, I can just calculate the first few equations, the first 3n minus m equations. And since I won't be calculating the rest, I won't be taking derivatives with respect to the generalized coordinates and generalized velocities that are constraints. I can enforce the constraints in the kinetic energy before. Since I won't be calculating derivatives, with respect to the constraint the last constraint generalized velocity. you see how in this equation here I enforce the constraint y is equal to 0, vy is equal to 0, and z is equal to 0, vz equals to 0. I enforce these constraints at the end. Since I'm not calculating these equations anymore, I don't need to enforce these constraints at the end. I can enforce the constraints in the beginning. I can go to the kinetic energy and set Vy and Vz are equal to 0 from up there. So I'm going to have names for the constraint kinetic and potential energies. I'm going to call them T tilde and L tilde. So that's the kinetic energy with Q1 to Q3n minus m minus 1. And then the rest of generalized coordinates, I'm going to set them equal to 0. And the same for the generalized velocities. So what are T tilde and L tilde? These are the constrained kinetic energy and constrained potential, constraint kinetic energy and constraint Lagrangian. So it's taking the kinetic energy and enforcing the constraint. The kinetic energy usually depends on both positions, coordinates, and velocities. So I'm going to say plus u1, u3n minus m minus 1, and then set the rest to 0, enforcing the constraints. The constraint Lagrangian would be the constraint kinetic energy minus the constraint potential energy. The constraint potential energy is usually potential energy only depends on positions, not on velocities. So it's just it's taking the potential energy plus enforcing the constraints. Okay. So again, if I'm not interested in calculating the constrained forces, I just want the equations of motion, then I can make a simplification early on by writing the constraint kinetic energy and the constraint Lagrangian, and I'll take a derivative of a simpler expression. Okay, so let's consider the simple harmonic oscillator again. Okay, for the simple harmonic oscillator, what does the constraint Lagrangian become? Remember, it's the simple harmonic oscillator enforcing the constraints that it is moving in the rectilinear motion. So y is 0 and z is 0. So this was the unconstrained Lagrangian. You see it here. What is the constraint Lagrangian? Vy and Vz are 0, right? And also y is 0. So I'm left with half mvx squared minus half kx squared. Okay, Lagrange's equations of motion now become d by dt del L tilde by del ui minus del L tilde by del qi is equal to F non-conservative forces dot with sum k del rk by del qi, but now I only goes from 1 till 3n minus m minus 1. So I'm not calculating the full 3n equations. I'm calculating the first 3n minus m minus 1. I'll get the equations of motion. One more simplification I can make to this equation is it's going to be uncoupled from the constrained forces. So this, in general, the non-conservative forces would be the constrained forces and the applied non-conservative forces. Okay? Yes?
Why is I going to 3n minus m minus 1?
Good question. Remember, we arranged our equation in such a way, we arranged ungeneralized coordinates in such a way so that the last m equations are the last m generalized coordinates are the last m holonomic constraints. So they're all equal to 0 when we enforce the constraint. When we write Lagrange's equations of motion, these last m equations, these are going to give us the constraint forces which enforce these constraints. And the others, the 3n minus m minus 1 other first equations, these are going to give us the equations of motion. So here what we're doing is we're restricting our attention to the equations of motion. Since we're doing that, we can enforce the constraints in the Lagrangian initially instead of enforcing them later.
I thought we had a total of 3n equations.
We have a total of 3n equations, but not all of them are equations of motion.
So
The last m, yeah.
So shouldn't it be 3n minus m?
3 minus m.
Because you're removing m equations, right?
That would be the first equation of constraint.
For the simple harmonic oscillator, wouldn't 3n minus m minus 1 give you 0?
What is it?
3n minus m minus 1 would just be 0.
Oh, let us think. So if I have one simple harmonic oscillator, 3n minus m minus 1, that will give us 3, and 2 constraints minus 1. So, oh yeah, so you're right. I should go to 3n minus m. You're right. And I had it somewhere else too. Here. Thank you. Okay, great. Thanks. Okay. Okay, so thank you. What I was saying is that Lagrange's equations of motion, using the Lagrangian, using the constraint Lagrangian, it's going to be decoupled from the constraint forces, so I don't even have to worry about the constraint forces. I can remove this from here. The first 3n minus m equations, the first 3n minus m equations are going to be uncoupled from the constraint forces, so these are just going to depend on the applied non-holonomic forces. Okay. So in most introductions to Lagrange's equations of motion, what you will see is this. What you will see is this equal to 0. To get to this equation, they are making a bunch of assumptions. Last of which is that there are no applied non-conservative forces acting on the system. If there are no applied non-conservative forces acting on the system, this is going to be 0. You get that this is equal to 0. Okay? But other than this assumption, there are a bunch of other assumptions that were made, that all the constraints forces acting on the system are holonomic, and that I have an arrangement of degrees of freedom. The first degrees of freedom, the first 3n minus m degrees of freedom are the unconstrained ones. Okay? So usually what you see in introductions to Lagrange's equations of motion in quick introductions are this equation equal to 0. Okay, so going back to the equation, to the simple harmonic oscillator equation, can we apply this equation to get the max minus kx equals to 0? We should be able to do that. So let's go back and let's apply this equation, that d by dt. D by dt del L tilde by del Vx minus del L by del x is equal, there are no non-holonomic constraint, sorry, there are no non-holonomic applied forces, so that's going to be 0. Del L tilde by del Vx is going to be d by dt mvx. Okay, minus del L by del x, which is minus kx. So we recover the equation of motion that we want. max is equal plus kx is equal to 0.
Why are we assuming dx is 0?
We're assuming what?
When we're calculating dl dx, we're assuming dvx dx is 0. Why?
d dx dx.
dvx dx.
d vx dx. Oh yes. When you take, yeah, we assume, it is an assumption that we make that the generalized coordinates and the generalized velocities are independent. That's why I didn't name them q dots. I named it u, which is a different variable. So there is no such thing of you taking a derivative with respect to the derivative of some variable. You have to take the derivative with respect to some new variable, which I called u.
It doesn't make any sense to me.
We'll talk about it again.
Is independent of the position in an oscillator.
Yeah. So why is Vx independent of x? Yeah, we're making the assumption that they are independent. I'm calling them different names. It's not x dot and x anymore. It's u and x, u and q. And here what I'm doing is I'm taking a partial with respect to q.
That seems like it introduces a contradiction, though, because how can it represent the velocity without?
Physically it does, but mathematically it doesn't. We'll talk about it later. Okay? Any other questions? Let's apply Lagrange's equations of motion to a simple pendulum, and if we have time, to a double pendulum. And when we apply Lagrange's equations of motion to a complicated system like the double pendulum, that's where it shines, basically. Its advantages shine. You don't have to calculate the constraint forces anymore between any two particles. You don't have to calculate the constraints. You can just go to the equations of motion directly. So let's do the simple harmonic oscillator. The simple pendulum. Okay, so I want you to write everything we did for a simple harmonic oscillator, do it for the simple pendulum. I want you to figure out what the constraints are, what are the constraints, what are the generalized coordinates, how to order them, how to calculate the kinetic energy, potential energy, constraint, unconstrained, forces, and so on. So try to go through the whole process, but for the simple pendulum. So yes, the first step, find the constraints and the generalized coordinates, constraint forces. Okay. Okay. What was your name? Right. It's your question. Okay. So, mathematically speaking, your concern is very valid. This is how mathematicians write Lagrange's equations of motion. The Lagrangian is in terms of two variables, q and u, totally independent. You take a partial derivative relative to q, and then after you take the partial derivative, then you substitute that u is equal to q dot. Same here. So you always, mathematically speaking, we're thinking of a function of two independent variables, q and u. I take a derivative relative to u, then I replace that q is equal to, that u is equal to q dot. When we derive Lagrange's equations from the calculus of variations, this is how we apply. This is this is what it is. Yes?
Sorry, so to clarify, q dot and u are both representations of velocity?
Yes, because at the end I set u is equal to q dot, but mathematically, strictly speaking, they're different coordinates. So it's like x and y. And then at the end I set y is equal to x dot.
Okay, so we're just solving a general system of equations using the Lagrangian, and we don't know that they're the same
Yeah.
thing, but then we make it kind of a special case for
Yes.
velocity. Okay.
Yeah.
That makes even less sense because if L is written as a function of q and q dot, isn't its partial
No, it's not q and q dot, it's q and u. You write, it's in terms of q and u, you take a partial with respect to q, which is completely defined. Then if you take the partial derivative, you replace q by u. Okay, so let's go back to the simple harmonic oscillator problem. What are the generalized coordinates here? What did you guys take them to be? Yeah, so the degree of freedom is theta. Theta, we said z and we said a, which was r minus l equal to 0 and z is equal to 0. These are the two constraints. The constraint forces. Okay, any questions with this? Constraint forces are, this constraint I can write as v dot ez is equal to 0. This constraint I can write as v dot er is equal to 0. Right? That's r dot is equal to 0, that's v dot is equal to 0. Yes?
Sorry, dumb question. Why do you use the letter A in this case? Is it just arbitrary curve?
Yeah, let's not confuse A with acceleration. Let me use beta. Beta. Yep. Okay. I can write my position vector here. R is equal to RER. So R, which is now beta plus L ER. What are the constraint forces acting on my system? Yes. Mu1 is E plus mu2 ER. Very well. And physically speaking, this is the normal force from the vertical plane, and this is the tension force in the chord, right? Okay. The velocity, if I can write the kinetic energy like this, I can write V as beta dot ER plus beta plus L theta dot E theta. Okay. Plus Z dot EZ. Plus Z dot EZ. I can write the kinetic energy now as beta dot squared ER, beta dot squared plus beta plus L squared theta dot squared plus Z dot squared. If I were to write the constrained kinetic energy, that would be equal to what? Yeah. What about the potential energy? It's just to the weight force, due to the weight force. So what is the potential energy here? Mm-hmm. Yes. What is it? What did you say? Minus mgl cosine theta. Right. And that's the same as the constrained kinetic energy. Minus mgl cosine theta. Yeah.
What's L and theta? Is L the length of the rod?
Yes.
Theta, you measure theta from the horizontal?
Well, this you should know. It's the angle between big X and small x.
And the beta is the change in
No, beta is just 0, R minus L. That's how I define beta. Okay? Now I can apply Lagrange's equations of motion. I can apply the, yes? The kinetic energy. This is the velocity. The kinetic energy is half mv squared. So this is an orthonormal basis, so I can just square each vector. What is it? Yes, thanks. Thank you. Okay, so if I just want to find the equation of motion, what can I do? If I only want to find the equation of motion, what do I do? Yes. So the d by dt del L tilde by del theta minus del L, del L tilde by del, call it U theta. So Q, yeah, it's U theta, UZ, U beta. The generalized velocity, which later on we will replace U theta by theta dot. But right now it's U theta. It's going to be equal to what? What is it? It's going to be equal to 0, right? Because that would be the applied non-conservative forces, which are 0 dotted with del R by del R by del QI, del theta. 0, okay. What is del L tilde by del U theta? Just to make it mathematically accurate, replace theta dot by U theta. We're going to take a partial with respect to U theta, then replace U theta by theta dot. Okay. So del L by del U theta is, well, L tilde is just S squared half M U theta. Right? And then minus plus minus MGL sin theta. There is a sign mistake, right? Yeah, the 1/2 is gone. But there's a sign mistake here. It should be a plus. It's because L is T minus U, so I already have a minus. And then I have a minus outside, minus inside, and the minus cosine theta becomes minus sin theta. I get a plus. It works out. So I will get M cancel out. I can replace U theta dot by theta double dot plus G over L sin theta is equal to 0, which is the equation of motion we know. And now, which equations would I need to apply to get the constrained forces? For example, which equation do I apply to get the tension in the cord? Exactly. I'm going to write Lagrange equations of motion with respect to the beta coordinate, and it needs to be the unconstrained equation. So d by dt del L by del beta U beta, right? F non-conservative, which here is going to be equal to F constrained dotted with del R by del beta. This will give me an equation for mu 2, which is the tension force. Does that make sense?
Tension's a constraint force.
Yes.
How do you differentiate between a constraint force and like?
An applied force. A constraint force enforces a constraint, you know, by its name. Like the weight force enforces no constraint. It's just a weight applied at a particle. It's an applied force. The spring force too doesn't enforce a constraint. Whereas normal forces, tensions, they enforce constraints usually by the particle needs to be on a certain surface, on a certain curve, or at a certain distance from another particle, or from something else. Yes. Yes.
I'm confused by the equation of motion step we were doing the partial derivatives. So
Yes.
we had the Lagrangian in terms of constraint t plus constraint u, or sorry, constraint t minus constraint u, right?
Yeah.
And then, but that's still in terms of only theta. So I was confused where the u theta comes back into the equation.
I replaced theta dot by u theta. So to make it more mathematically accurate, you take a partial derivative with respect to u theta. Then at the end, you replace u theta by theta dot.
Yeah, that's why I was confused, because if we wait until the end to make it mathematically accurate, then the original equation doesn't have any thetas in it, so the partial derivative should be 0.
Wait, are we waiting until the end to make the equation accurate? Where? How?
Well, you said that we wait to make it mathematically precise. We usually do the partial derivative in terms of u theta first.
Yes.
But my confusion originates because in the formula we created for the Lagrangian, there is no instance of u theta until we replace it. So then, would that make the partial derivative 0?
Which formula we created for the Lagrangian? Which formula are you referring to?
When we took the constraint t minus constraint u, which kind of gives us our RL squared.
Yeah. So that was a mistake. That at the beginning we should have had t and u in terms of the u's and q's rather than the q's and the q dots. So let's agree on this. To always write the Lagrangian in terms of the q's and the u's, initially take the partials and then replace.
Okay.
Yeah.
Okay, so the problem originated when we substituted back in theta dot earlier.
Yes.
Oh,
Yeah.
thank you.
Yes. Yes. Okay. Okay, so we are familiar with the Newton-Euler equations of motion. For a system of particles, for each particle you have that Fi is equal to mi ai. These are the Newton-Euler equations, or Newton's equations. The balance of linear momentum. Right now we introduced Lagrange's equations. Okay, and these are all balance laws. They're introduced as laws, and they're not derivable from any other equations. They're introduced as laws. Now, sometimes instead of introducing a law, an equation to find the motion, what people do is that they introduce a concept. They propose, for example, a minimization, meaning that, for example, Hamilton's principle says that the equations of motion for a system of particles, or the motion of the system of particles, is going to minimize or is going to extremize an action integral. So he defined this integral, called it the action integral. It's basically the integral of a Lagrangian. LDT from T0 to T1. So Hamilton's principle says that the motion of a system of particles minimizes the action integral. Okay. We can show mathematically using calculus of variations that minimizing this integral, L is the Lagrangian, that minimizing this integral gives us back Lagrange's equations of motion. We can also show using calculus that Newton's equations and Lagrange's equations are the same, are equivalent. That's Hamilton's principle. There is also D'Alembert's principle and the principle of virtual work. Okay, so the principle of virtual work applies for statics, a static problem, and D'Alembert's principle is an extension of the principle of virtual work to dynamics. What this principle says is that if I have a constraint acting on the system like we've had initially, if we have a system with constraint f1.v1 plus so on, fn.vn is equal to 0, then it needs to satisfy this D'Alembert's principle, which says that fa1 okay. And this principle of virtual work, or D'Alembert's principle, can be easily shown, not easily, but can be shown, I have it in the notes, that it's equivalent to Newton's equation. What does it say practically? This equation says these vectors D, sometimes they're written like this, delta R1. They mean virtual displacements. And when we're dotting a force with a virtual displacement, a force started with displacement is what? Work. So what this principle is saying is that the work of all the forces, so here they take the force minus the MA. So they're taking kind of a force minus a fictitious force that is MA. Whatever, they're saying that the work of this combined new force, the sum of all the works of all the forces is 0. So that's why it's called the principle of virtual work, because it involves work, because it involves some forces dotted with some fictitious displacement, virtual displacements. Okay. And then this can be shown to be equivalent to Newton-Euler's equations. So there are different principles of mechanics, dynamics, that start from different places and lead to the same thing. There are also equations of motion, Gibbs-Appel, Maggie's equations, that can also deal with non-holonomic constraints. Remember the non-holonomic constraints we started the lecture with? Constraints that are written in terms of velocities only. And different equations have different advantages. They decouple equations in a certain way. They get to the equation of motion directly instead of manipulating a set of equations. So hopefully this was a little bit interesting, illuminating to the other formulations of equations of motion out there. Okay? Thank you all for coming, and see you next week.